Chapter 5, Magnetostatics. Let's get to it. There's a whole bunch of stuff. Full video somewhere else. Go find it. This is the Lorentz force. A moving charge in a magnetic field experiences a force, and then you can also have the electric force too. If it's a wire, each little piece of that wire experiences a force. You actually have to integrate over the whole thing. Here's an important thing. We have a moving charge QV. That's the same as I dl. That's the same as K dA. K is the surface current density. That's the same as J dV. That's the charge current density, volume per area. Now we get to the magnetic field due to moving charge. It's B on Savart, which says mu naught over 4 pi, QV cross R hat over R squared. And I can replace QV with IDL, but then I have to integrate over the whole wire, so I get that. And then, well, what if it's a volume thing? Then I can replace QV with JDV, but then again, I have to integrate. Now, in electrostatics, remember we defined the electric potential V based on the curl of E being 0, and then we have Gauss's law right there. And that got us this Laplacian and our definition of electric potential. In magnetic fields, we have Ampere's law, which says if you integrate B dot dl around a loop, it's equal to the current passing through an area bounded by that loop. And that gives us the differential form, which says that the curl of the magnetic field is mu naught J, and there is no divergence in the magnetic field. Del dot B is 0. But because of this, we can pick a scalar potential A such that that's still true if we define B as del cross A. B is the curl of A, where A is the vector potential. Picking this special choice of the divergence of A is 0, we get this vector Laplacian equation that looks like this equation. So that means that the solution to A is like the solution to V, but it's a vector. So here we have the vector definition of the vector potential. It's the mu naught over 4 pi current density dV over R instead of just the charge density. We can also use that to define our magnetic dipole moment, which is very similar to the electric dipole moment due to a potential, but it's a vector. And then we can find the magnetic dipole moment of a magnetic field, which looks identical to the electric field due to a dipole, which is really important later on. So there you go. If you want the full video, there's somewhere on there, either linked to this or in my playlist. Talk to you later. Bye.